Hi, good morning. This is Srinivas Alwala, working as Assistant Professor in the Department of Computer Science and Engineering, SR Engineering College, Warangal, Telangana, India. Welcomes you to the presentation and structure of a switch in data communications and computer networks. And before we know how a switch is structured or designed, let us know the course objectives. Course objectives are: the students will be understanding the switch structure designing, understands the need of different types of switches used in networking. The outcomes of the presentation are: at the end of the course, the students will understand what is the need of switch designing to improve the network performance, how and knows and illustrates how a switch can be designed to make it more efficient to improve the network performance. Now coming to the structure of a switch. We know we use switches in circuit switch network and packet switch networks. Here we discuss the structure of switches used in each type of network. Circuit switching uses either of the two technologies. One is the space division switching, the time division switching. Whereas space division switch, the path in the circuits are separated from one another, spatially designed along analog but currently used in both analog and digital networks. Look at the picture here. The basic structure of a switch, what we call it as a crossbar switch with 3 input lines and 4 outputs. A crossbar switch connects n inputs to m outputs in a grid using micro switches called as transistors at each cross point. The major limitation of this design is the number of cross points required to design a crossbar switch. To connect n inputs to m outputs using a crossbar switch requires n into m cross points. For example, to connect 1000 inputs to 1000 outputs, a switch requires 1 lakh cross points. A crossbar with this number of cross points is impractical. Such a switch is also inefficient because the network statistics show that in practice fewer than 25% of the cross points are in use at any given time. The rest are idle. So to overcome the problem of the crossbar switch, we go for designing a multi-stage switch. That is the solution to the limitations of the crossbar switch, in which combines the crossbar switches in several stages. A multi-stage switch is a solution to the limitations of the crossbar switch, which combines crossbar switches in several stages, normally a 3-stage switch. In a single crossbar switch, only one row of column is active for any connection. So we need n into n cross points if we can allow multiple paths inside the switch. We can decrease the number of cross points. Each cross point in the middle stage can be accessed by multiple cross points in the first or the third stage. Looking at the picture here, a capital N number of channels are going to be divided or broadly categorized into small n number of channels, and small number of channels are being linked to a crossbar switch used in the first stage. And the number of output lines from the first stage crossbar switch are the number of switches used in the middle stage. And every middle stage switch has an output line and an input line from the first stage switch and an output line to the third stage switch. So at the first stage we go for having n into k cross points for every switch. In the middle we have n by n into n by n cross points in the crossbar switches, and in the third stage we have k into n number of cross points in the third stage. So following are the steps to design a multi-stage switch. Divide the n input lines into groups, each of n lines for each group. We use one crossbar of size n into k, where k is the number of crossbars in the middle stage as previously said. So n by n crossbars, n into k cross points. We use k crossbars, each of size n by n into n by n in the middle stage. We use n by n crossbars, each of size k into n at the third stage. So the total number of cross points needed to design a three-stage or a three-stage multi-stage switch are n by n into k plus k into n by n into n by n plus n by n into k into n, which is equal to 2k capital N plus k capital N by n whole square. One drawback of the multi-stage switch, looking at the designing of the multi-stage switch in the previous section, is there is one drawback. The drawback is that blocking during periods of heavy traffic. As we see previously, a single crossbar switch off is n into m outputs, that is n into m. If at all we go for taking an example of 10 inputs and 10 outputs, we go for getting 100 output points, 100 cross points. But if at all we go for designing a three-stage switch where the number of cross points is going to be less than the 25% of the cross points needed for the data communications, so there raises a blocking during periods of heavy traffic. The idea of multi-stage switch is to share the cross points in the middle stage crossbars, which can cause a lack of availability when the resources are limited and all users want a connection at the same time. When one input cannot be connected to an output because there is no path between them, all the possible intermediate switches are occupied. To overcome the blocking in a multi-stage switch, that is in a three-stage switch, the total number of cross points is 2kn plus k capital N by n whole square, which is much smaller than the number of cross points in the single stage switch as we discussed earlier. So we take an example of designing a three-stage switch of 200 into 200 where n is equal to 200 with k equal to 4 and n equal to 20. In the first stage we have n by n or 10 crossbars, each of size 20 into 4. In the second stage we have 4 crossbars, each of size 10 into 10. In the third stage we have 10 crossbars, each of size 4 into 20. The total number of cross points is 2kn plus kn by n whole square or 2000 cross points. This is 5% of the number of cross points in a single stage crossbar switch, where 200 into 200 is equal to 40,000, which raises a problem of blocking at the time of overflow of data over the networking. To avoid the blocking in a non-blocking situation, as the clause criteria has been to be implemented, that is the number of middle stage switches must be at least 2n minus 1. Clause investigated the condition of non-blocking in multi-stage switches and come up with the following formula. In a non-blocking switch, the number of the middle stages must be at least 2n minus 1. In other words, we need to have k is greater than or equal to 2n minus 1. According to the clause criteria, the number of input channels for a single crossbar in a multi-stage switch need to be, that is n is equal to capital N by 2 under root, where k is equal to greater than or equal to 2n minus 1. Generally we assume that k is equal to 2n minus 1 cross points, 2n minus 1. The total number of cross points are equal to 4n 2n under root minus 1, which is generally equals to the 25% of the cross points needed for the data communications, which solves the problems which has been arised in designing a multi-stage or a three-stage crossbar switch.